My name is Stephen Slaughter, and I am today's temporary host for the USGS Landslide Hazards Program Seminar Series. Your usual host, Matt Thomas, is in the field and will return next week. During today's presentation, please remember to keep your microphones muted and video off. We ask the speakers to reserve 10 minutes before the top of the hour for questions. So following the presentation, you can submit questions via the chat function, or preferably use the raise the hand feature to ask questions using your microphone and camera. Today's speaker is Andrew Graber. Andrew completed his BS in geology at Wheaton College in Illinois and is currently a geological engineering PhD candidate at the Colorado School of Mines working with Paul Santee. His research thesis, which he'll be discussing today, focuses on understanding rockfall frequency and depositional behavior from natural rock slopes. In addition to his thesis work, Andrew has published papers on design methods for post-wildfire erosion mitigation and on modeling-based investigations on critical groundwater conditions for large landslides in southern Peru. Andrew received the 2019 AEG Marlife Scholarship and has received research and fieldwork grants from AEG, GSA, the Wyoming Geological Association, and the Colorado Scientific Society. So welcome, Andrew, and the virtual stage is yours. And I turned on the transcript. Let me turn the transcript off here. There we go. Okay, Andrew, sorry, go ahead.
Sounds good, no worries. Thanks, Stephen. Just to check as I get started, are you seeing my mouse pointer on the slides?
I am not seeing it.
Laser pointer should work then.
Are you showing it?
Yes.
Do folk? I don't see it, unfortunately.
Cursor. Well, we can probably get away without that. Anyways.
Okay.
Well, thanks, Stephen, and thanks to the USGS Landslides group for inviting me to talk here today. So what I'm hoping to accomplish in this talk is to talk a little bit about my thesis research, but I also want to talk about this this subject of rockfall frequency because it's kind of a niche topic, but it's an interesting one from a geomorphic perspective, and it's an important one from a hazards perspective. And so I hope to be able to give an overview of a little bit of the theory, some applications that other people have done to try to assess rockfall frequency in various ways, and then to talk about the particular case studies in Glenwood Canyon that I've been a part of. So to start off with some acknowledgements, I wanted to thank my advisor, Paul Santee, whom I've been working with for several years now, and whose help has been invaluable. And then some folks at CDOT, Matt Tello, Ty Ortiz, and Bob Group, who've been helpful organizing funding for me, but also making sure I have access to facilities in the canyon. Folks who've helped me in the field, Claire Graber, my wife, Julia Payne, Josh Klein, and Kyle Raddick, who are all School of Mines alums who helped me with field work. And then for funding, School of Mines, Colorado Department of Transportation, Colorado Scientific Society, AEG Foundation, Wyoming Geological Association, and GSA. So we'll talk about rockfall frequency as a topic. I'm going to talk about some established methods that people have already published to evaluate rockfall frequency, to quantify it. And then I'll give some background on my study area, and I'll talk about these two case studies from my thesis research, both in Glenwood Canyon, looking at rockfall frequency at the same sites, but using two different methods. So rockfall is this erosional geomorphic process, and it's also a hazard. And when we talk about rockfall, there are a couple of ways to think about characterizing it. So one is this parameter of frequency, and as you'd expect, that refers to the frequency of how many rockfalls are happening per year. But like with other geologic events like earthquakes and floods, and landslides, rockfall frequency is tied to rockfall volume. So the way that we quantify it, the best way to quantify it is to quantify it in that context in a way that includes volume. So the way that people have usually or have often done this, not every study, but a common way to do this is to use a frequency magnitude curve, like you might see for floods or earthquakes. So what that plots is magnitude, in this case volume, on the x-axis versus frequency on the y-axis. And you can see a bunch of different kinds of parameters on the y-axis here: cumulative frequency, frequency density, which is just frequency normalized by the bin width of your histogram, probability of exceedance, a number of different parameters, but this relationship still holds up. So what people have observed when they plot up rockfall data this way is that there, in log-log space, there's this linear relationship, which is quantified by a power law. It's not a linear regression, it's a power law regression. And what that does is you can use the coefficients of the power law fit to that data to describe the trend of rockfall between frequency and magnitude. And this plot also shows something that people have often observed, which is that there's frequently sort of a drop-off of data towards the lower end of the volume spectrum. And that's related to what people usually attributed that to is in their rockfall databases, the small events get undersampled. And so that's why they fall away from this linear trend, where in theory, the linear trend should continue all the way down to 0. So other options for quantifying rockfall frequency, people would use a recurrence interval like with floods or earthquakes, but those also have to be tied with magnitude. And as you probably all know, recurrence interval is basically just the inverse of frequency. And so then the other side of this is, where is rockfall happening? On the talus deposit? Is it running out beyond the talus deposit? And so that's another piece of this this topic that's important to consider and is usually a part of what people are looking at in these frequency studies. So I'm going to talk about a little bit of literature review of studies where people have looked at rockfall frequency and depositional behavior in order to get timing information, magnitude information, to better understand these processes. And note that a lot of studies use a combination of methods, but I've broken the big methods into a couple of categories. So one is to look back at some kind of a historical record of rockfall and to be able to make calculations based on a database that way. So using actual historical records where people have written down the times and locations and volumes of rockfall, dendrochronology, using tree rings, cosmogenic isotopes, lichenometry, all to date old events. And your other main option is to directly measure rockfall and create an inventory that way. So change detection methods are becoming more and more popular. Seismic monitoring is another one that's been used in at least some fields, and we'll talk about that. And then there are a few other options that are out there that are published. I'm not going to talk about them in any detail in this presentation, but I can send you some references if you're interested. Feel free to contact me. Terrestrial SAR, rockfall collectors, using radiocarbon under select conditions. So those are some of the other options. So historical records are great for computing rockfall frequency, but they're hard to get. So they're easier to find along transportation corridors, or if there's a specific site of interest. Yosemite Valley is a good example of a place where there's a pretty extensive rockfall record. But the detail and availability of these records can be highly variable. And sometimes a record will have, for some events, it'll have all the information you want, and it won't have that for other events. And these are often biased towards larger events simply because those are the ones that are more likely to make it all the way down the talus and impact a road or a facility that somebody cares about. So this plot on the right is from an example in British Columbia where they had 2 transportation corridors, and along each of them there were rockfall records from both a road and a railroad, and so they could plot up frequency magnitude data and be able to compare them along two corridors and have two data sets to look at each corridor. And so they got the sort of plot that we're talking about, this linear relationship in log-log space. There's a little bit of this tailing off towards the smaller magnitude events. But they found some pretty nice agreement between their first corridor, the highway and railroad, and the second corridor, their highway and railroad. And so if we look at these B parameters, to put these in context, if the B parameter is greater, that means your curve is steeper, and that means the relative contribution of small events is greater. And so that's how you can start to compare these curves between databases. And this was a case where they had some independent dates from some rock avalanches in the area, and so they were actually able to extend up to some very large volumes in their plots that way. So dendrochronology, well, I guess I'll start off by saying, what if you don't have historical records of rockfall? How do you build a database using some other kind of record? So one example is using dendrochronology. That's basically counting ages with tree rings. And this is a pretty well-established age relationship. And when you take cores of trees, if your core intersects any sort of disturbance that might have been caused by rockfall, like a scar in the bark or a year where the growth ring is thicker because the tree was reacting to the trauma, you can use that to build up a rockfall database. So you need to have relatively dense, long-lived trees, and it takes a lot of effort, but it gives you this opportunity to look at spatial distribution of rockfall. So this example is from Switzerland, and they had a database of trees. Those are these little dots in the upper left plot in kind of the colored area. There's some black and gray dots. So those are marking locations of trees. And so the color ramp in this central part of the map is showing the recurrence interval between growth disturbances. And so that's what they're using as the proxy for rockfall events. And it means that they're able to develop recurrence intervals for growth disturbances at each tree and then contour those values so that they have a plot of recurrence interval as it varies across the talus deposit. So what they showed, and then if you look down at the plot below that, they were able to identify the same damaging event in a whole bunch of trees all the way down this north end of the talus deposit. So they said, while most of our events are relatively small incremental rockfalls or fragmental rockfalls, we have record of one large event that made it all the way down this talus deposit and damaged a lot of trees on the way down. So this is a method that's not precise enough to capture year-to-year variations in rockfall, but these more decadal type variations you can detect with dendrochronology. So lichenometry is another option for trying to build a database of old events. This is a quaternary dating method from glaciology, and it uses calibrated lichen growth rates to infer minimum surface exposure ages. So what that means is you develop a calibration curve that characterizes the relationship between lichen size and lichen age. And people do that by dating surfaces where they know how old the surface is and they can measure a lichen on it. And then you go to places where you don't know the age of the surface and you measure the lichen size and compare it to that curve to get your age estimate. The accuracy can be a bit limited, and the age ranges as well to a little bit longer than dendrochronology, but still in the last 1,000 to 2,000 year range. The upside is this is a method that lets you collect a lot of data very quickly because you're just collecting lichen measurements. It assumes that the rock surface was clean prior to growth. And there have been some concerns raised about lichenometry. These are such long-lived organisms that people are concerned, how well do we actually understand the lichen growth? How linear is it? Or how consistent is it, I guess? And so that's worth acknowledging here. but there is a fairly well-established relationship between age and size, and so you can still say some things about, well, larger lichens are older. So this is a case study from the Austrian Alps, where they had a really large lichenometry data set for a whole bunch of talus deposits, and the map on the right is showing those deposits there. And I think someone is unmuted. I'm gonna mute. There we go. We've still got someone unmuted here. I'm getting some.
Could someone, everyone please check and make sure you're muted.
I'm just getting some feedback on my speakers.
Yeah.
Okay, that's better now. Thanks. So in this case study, they had lichenometry measurements from a whole bunch of talus deposits, and what they were able to show is that they were looking at lichen coverage to say, well, at the tops of these talus deposits, there's a lot more rocks that are all free or almost totally free of lichens. So we're using that as a proxy for greater activity at the tops. But they also found an association between these more lichen-free fans and permafrost. So they were able to associate, well, these permafrost-affected slopes are causing more rockfall in certain places around our study area. And they were also looked at the calibrated lichen ages, and looking back, they were able to find this peak. If you look at the left-hand histogram down at the bottom of the slide, so that peak around 1890 or so, they associated that with increased rockfall activity at the end of the Little Ice Age, giving you more lichens that were from that time period. And so they were able to show a little bit of temporal variation that way as well. Another way you can get the ages of previous rockfall events is with cosmogenic isotopes. This gives you a good age range. It also makes that assumption that you have a boulder that was it was buried so deep it was not having any cosmogenic ray interactions, and then the rockfall happened and it was exposed. This is a method that's more expensive, and it takes a lot more effort to get your samples and do your sample processing. And so that's why it can be difficult to get a big enough data set to actually build a frequency magnitude curve. But there's still some things you can learn. So this is a case study from Greg Stock's work in Yosemite. This is from a paper that's kind of a park-wide hazard assessment for Yosemite. And so they collected beryllium-10 cosmogenic ages for outlying boulders. And so what they meant were boulders that were beyond the edge of the talus deposit, but were still obviously rockfall related, and were also tended to be in and amongst some of the campgrounds and like facilities that already existed in Yosemite Valley. And some of these are really quite large. There's a picture of one on the upper right. So they collected these beryllium-10 ages and plotted them up. And what they found a couple of things. So one is that all of the ages fell below their 15,000 year expected cutoff, because that's the inferred age for the deglaciation of the valley. So all the rockfalls came out as younger than that, which makes sense. And that allowed them to use that 15,000 year upper age estimate to get a recurrence interval for their total data set of outlying boulders. And so if you take 15,000 and divide it by 258, you get 50 to 60 years on average. Okay. So if we switch over to the idea of directly measuring rockfall with change detection, or rather, change detection is a method that's becoming a lot more popular these days as technology becomes more available and more usable. So what I'm referring to with change detection is taking 2 point clouds. If you look at the graphic on the lower right, taking 2 point clouds where in the left panel, it's showing computing a normal to the first point cloud using some size neighborhood of points. And then in the right panel, it's showing how you then align a cylinder along that normal and average the points in the two clouds so that you can actually calculate the difference between those two clouds along that line. So when you repeat this kind of calculation thousands or tens of thousands or of times for an entire point cloud, it means you can map change across a large surface. And so I'm sure many of you are already aware of how powerful of a technique this is. So you can do change detection on point clouds developed using LIDAR or structure from motion photogrammetry. For those of you that don't know, photogrammetry is this technique visualized in the upper right, where you take repeated overlapping photos of a subject with a moving camera, and then a computer algorithm reconstructs the shape of your subject based on the motion of those cameras and identifying the features in multiple frames. So photogrammetry is a cheaper version of preparing point clouds, but you've got issues with removing vegetation, and you've also got to be very careful about how you scale the point cloud. If you use scale bars or GPS ground control to tell the model what the dimensions should be in real life. LIDAR gives you very precise measurements, but is more expensive, and so it can be more difficult to apply. But both of these give you point clouds that let you detect changes down to the centimeter scale, which can be really powerful for detecting rockfalls, since all the methods we talked about before pretty much leave out all the things at the small end of the volume spectrum. So this is a photogrammetry case study from a pit mine in Australia, where they had several monitoring periods where so the top image is showing the pit slope they were monitoring, and the colors are representing different periods of rockfall monitoring. So you can see all the rockfalls that happened in periods A1, A2, etc. So they detected a total of 645 events on the small end of the volume spectrum from February to March 2018. And so then they were able to prepare frequency magnitude plots. And this is a point where you can start to see a few of the differences here. So this red line is showing a period of lower activity, while the blue and orange lines are showing periods of higher activity. And they associated the higher activity with wet periods, and then also with extremely dry periods when they had these weak siltstone and clay stones drying out and contracting and fracturing more because of that. These figures are from a LIDAR change detection study where they had several monitoring periods, but I think about a year of it, they took hourly LIDAR scans of this coastal bluff in England. And what that allowed them to do was compute their frequency magnitude plot, that's the left of the upper graphs, at several different time intervals. So, and by the way, on the y-axis, you're seeing the probability of exceedance instead of what I put on, or what was on the previous plots with frequency, but the power law relationship still holds. So this is showing how if you monitor at a shorter time interval, your frequency magnitude curve gets steeper because your relative contribution of small events is greater and the large events is less. And that's because when you have frequent rockfalls at a slope, often rockfalls will happen from the same location on the slope repeatedly. And so if you scan those at a year apart, it might look like just one event. But if you were to scan it every month of the year, you might see it was in fact 5 different events that all just occurred in the same place. So you see, with more frequent scanning, you see more smaller events. And then the plot on the right is showing the change in the B parameter for the power fit with the change in the monitoring interval. So I wanted to say just a quick word on seismic sensing for rockfall monitoring. A lot of the case studies that I've looked at for this applied seismic monitoring of rockfall in volcanic settings, where they were looking at a lava dome and monitoring rockfalls from the lava dome to to use as a measure of volcanic activity, whether that's the extrusion rate of the magma, or if it's related to seismicity in the magma chamber. So this plot in the lower left is showing how rockfall activity was increasing, and they were able to correlate that with some other signs of volcanic activity. I'm not aware of any examples that took a seismic plot or a seismic record of rockfall and created a frequency magnitude plot from it. And I think that's because of some concern over estimating the volume from the seismic amplitude, because the amplitude is dependent on how close you are to the seismic event and some issues like that. So now that we talked about the literature review, that's kind of a quick view of a whole variety of ways to look at rockfall frequency. And so with those things in mind, I want to switch gears and talk about these case studies that I've worked on in Glenwood Canyon. So what I'll start with is to talk about background on the study area itself. So any of you that are already in Colorado or have explored the West may have some familiarity with Glenwood Canyon. So this is a transportation corridor for Interstate 70, as well as the Denver and Rio Grande Railroad in western Colorado. It's a 13-mile long stretch of the interstate. And Glenwood Canyon suffers from really frequent rockfall problems. And I'm sure you've all heard as well about the debris flows that have happened in Glenwood Canyon this past summer. And rockfall has been a problem in Glenwood Canyon ever since people started putting roads through there. So the geology of this area, we're just going to talk about the geology of the lower part of the canyon, because that's what's relevant to the rockfall studies I've been doing. So at the base, there's the Precambrian basement. These are metagranitoids, sometimes intruded with some other younger granite dikes. And then above that, there's two Cambrian formations, the Saguache orthoquartzite and the Dortsero dolomites. And these form the base of the White River uplift. So that's what the Colorado River cuts through to form Glenwood Canyon. So last year, the Grizzly Creek fire burned part of the canyon itself, as well as Grizzly Creek Canyon and much of the White River uplift in the vicinity of Glenwood Canyon. And we'll talk a little bit more about that later because that's more relevant to the drone scanning study. But that's another piece of our context here. So I like to include this picture because it shows some of the motivation for studying rockfall in Glenwood Canyon at all. So there are plenty of cut slopes in Glenwood Canyon, and as you all know, cut slopes are a frequent source of rockfall. But this is a place where we actually have a lot of rockfall from natural slopes. And you can see the proximity of these. So the big slope above the tunnels to the right, that's all the Precambrian granites and metagranites. You can see the proximity of these kinds of slopes to our transportation facilities here in the canyon. So for the first case study, we studied 6 cliff and talus deposit systems in the Glenwood Canyon area. Those locations are marked by the orange points in this map. And then the background shading is just a slope map, and that's really just to show the relief of the canyon. So you can get an appreciation for it. So these slopes, 4 of them are granite rock masses. There's one orthoquartzite rock mass, and then another one that has another talus deposit that has sources that are both granitic and orthoquartzite. And we chose the locations primarily for access because they were near to places where it was possible to park and get out and walk to these slopes to collect data. So we chose to use lichenometry to quantify rockfall frequency because we don't have much of a historical database, even with all the focus on Glenwood Canyon to clean up rockfall hazards. there's the database is really limited. I have a copy of part of it, and most of the events, there's no volume recorded for it. So we have timing information, but no volume. So that doesn't help us for frequency magnitude. We don't have enough large, long-lived trees for dendrochronology. We're in a deep canyon, so cosmic ray shielding is problematic for cosmogenic dating. And the other upside of lichenometry is it's just a lot cheaper than any sort of direct methods that require advanced equipment. And in addition, this was so I did the field work for this in 2018, and even in the few years since then, photogrammetry technology especially has been getting a lot cheaper. So, so to collect the data for this, I measured lichens on boulders at each slope and sampling along the contours, and we'll look a little bit more at that in a moment. So these images are showing the study sites from this project. The red dashed lines are outlining the source areas, and then the talus is below in each photo. And then the letters are indicating lithology. So G for granite, Q for quartzite. So as I alluded to earlier, with lichenometric studies, to get your estimated ages, you have to have some understanding of what the local growth rate is for your lichen species, because since lichens are living organisms, they're affected by climatic factors that can change their growth rate. So theoretically, you can get calibration data from any surface that you know the age of, which could be a foundation or a monument or a quarry wall, or there are a whole bunch of possibilities. But most frequently, the known age surface information comes from tombstones in local cemeteries, where you have a date right there on the gravestone. There's some uncertainty with gravestone ages, just because they might have been put up a few years later after someone died, or a few years early, but it gives an okay approximation of age. And so then you can start to develop these curves, which I've put in the lower right, that are plotting the relationship between surface age of these known age surfaces and then our lichen long axis. So to get our calibration curve, we plot a linear fit to the fastest growing lichens. So those are marked by the little crosses. And you can see that this data is a little bit limited. And so that's worth bearing in mind, that our calibration curves are not very well constrained. And so it's just, so that's an uncertainty in our calculated ages. So for the data set, there's I have 1,200 lichen measurements from these deposits. And so these histograms on the right are summarizing. Oh, and I forgot to mention, the reason I have two columns over here on this slide is because I have two species. So the idea behind choosing two species was that we could collect two semi-independent lichenometry data sets and then be able to compare, do they show the same picture about rockfall or do they not? And we'll have sort of a semi-independent check on our results. So that's why these and some other subsequent plots are color-coded, where the brown is for one species, Lecidea atriburnea, and the green ones are for Lecanora novomexicana. So the histograms are showing our lichen data after we've converted the size measurements to ages. The data set represents over 1,000 boulders, with a few that have volumes up to 24 cubic meters. That was the largest one. And then a note about an assumption in this method. This method is assuming that every block in the talus is its own rockfall event. And as you can imagine, that is an assumption that's more likely to be true for small blocks, which theoretically are less likely to shatter, and less true for large blocks. So that's another assumption. We have to make it with the precision of lichenometric dating, it's not really possible to date 5 adjacent boulders and tell for sure whether they all came from the same rockfall event or not. So that's an assumption to list here. So this gives us frequency magnitude curves where we've plotted our rockfall volumes. Those are from the boulder size measurements. And then on the y-axis is frequency density. So that's our frequency where we've computed, we've binned the lichen sizes based on volume, divided the oldest age in that bin by the number of measurements in the bin, and then further normalize that by the width of the bin. So that's why it's frequency density instead of just frequency. So that gives us our frequency magnitude curves. With some of these, there's pretty good agreement between the two species at a given slope, slope 1 and slope 2. With others, there's a little bit more divergence. And another thing that you can observe about these plots is that the data start to fall away from the curve towards larger magnitudes. And we attribute that to the undersampling of the large volume rockfalls, because we're assuming every boulder is its own rockfall, and larger volumes are just going to be more likely to disaggregate. You know, a 24 cubic meter boulder is pretty large for this area, given typical rock mass characteristics. So from the frequency magnitude curve, we can calculate recurrence interval, which is just 1 over our frequency, and that lets us get recurrence intervals for different volumes of rockfall. So these are color-coded. So the blue is for a 0.1 cubic meter rockfall, 1, 10, 100 cubic meters. And then each of these is grouped because we've got our 2 species estimates again. So the picture is pretty consistent at the smaller volumes. Our recurrence intervals in years are in the 1 to 10 year range. But once we get into larger volumes, there starts to be a lot more scatter. There starts to be less agreement between the species, and that goes back to the mismatch in our frequency magnitude curves. One thing that's curious about this is that so slope 1 is one of our quartzite slopes, and that looks very similar to slope 2, which is a granitic rock mass. And just from looking at them, it would be reasonable to conclude, well, the quartzite one should have more frequent rockfall, right? Because it's much more frequently jointed. And so that's one of the things that was a little bit curious, and that I'll come back to with the drone study, because that's one of the things we're looking to check is, does this result actually make sense? If we plot up the lichen ages spatially, it gives an opportunity to try to look for patterns in deposition to see, are we seeing older ages at the top of the deposit and younger ages at the top and older at the bottom. And the patterns are not very clear in this data. So we conclude that to indicate that our rockfall activity over the time span that we can look at here, which is going back in these plots, the oldest age is about 500 years. In that time span, rockfall at these slopes is dominated by these smaller incremental rockfalls, instead of a large event that might bury a whole side of a talus deposit. So then to put these talus deposits into a longer term, like geomorphic context, we wanted to know, how does the volume of the deposit relate to the frequency magnitude information that we have? Basically, to back out, if this is our frequency magnitude curve, how long would it take us to get all of the volume of talus that we're observing at these deposits? So we were looking at Glenwood Canyon here. This is an oblique image to illustrate how talus tends to fill these chutes and gullies in these granitic bedrock slopes, rather than forming cones or big aprons of material. There's some of those kind of cases, but we didn't really find a volume estimation in the literature that matched the slopes that we had, and so we came up with some new ones to try to model if we have this gully and we fill it with talus and it's basically bounded by bedrock, what kind of volume does that give us? And so once we get the volume estimate, then we can back it out to find out what kind of time span of deposition are we looking at. So to illustrate how we get the volume, this plot on the right is showing, here's the outline of our deposit. Here's the DEM in part B. Here's the DEM of the deposit surface. And so if we estimate what this channel steepness is from the bedrock slopes around the deposit, and we get we use the interquartile range of these bedrock slope measurements to get a steeper channel a steeper chute and a shallower chute, so that we have an upper and a lower bound volume. And then in the lower group, it's just showing the DEM put together with the lower surface, and that's what we use as our deposit volume model. So this upper right plot is showing the volume ranges that we estimated for each deposit. So those are varying between about 10,000 cubic meters all the way up to between 400,000 and 700,000 cubic meters. That's a much larger, more extensive deposit, slope 6. And so we found an equation that can use the frequency magnitude parameters A and B and an estimate of your largest and smallest possible rockfall sizes to calculate a volumetric flux, which we then we took that and we divided our total volume estimate by that flux to get our accumulation time. And we constrained this max volume using some measured events. So there's a rockfall that hit the highway in 2004 from the quartzite that was about 1,100 cubic meters, and then a 2010 rockfall of about 450 cubic meters from the granitoids. And so these are our estimated accumulation times from those, and we have some good overlap with some of these, and some not so great overlap or lack thereof for some of the other slopes. And so that goes back to the shape of the frequency magnitude curve, and where we have mismatch between the two species in those curves, we get a bigger possible range for our accumulation time. So we have these recurrence interval estimates. Some of them seem to make possible sense. A 1 cubic meter rockfall every few years seems reasonable given the amount of lichen coverage on these deposits, the amount of scars on boulders from recent rockfalls. So we have those estimates. We have this picture that the smaller rockfalls are dominating over our evaluated time scale, and that it's a fairly random depositional pattern at that 5-century type time scale. And we have these times that we estimated to accumulate the talus volumes. But these left us with some more questions about, well, how do we know for sure that these results actually make sense? How do we validate this with an independent method that's not dependent on lichen growth? And so that's how we got to doing a drone study in Glenwood Canyon, and I'll talk about that in a minute. I just wanted to acknowledge some of these uncertainties about when you measure a lichen date, you're assuming that it grew since the surface was exposed, but maybe there was a lag in that time. And we also have, we know there's some uncertainty in our calibrated growth rates, and our larger events are probably undersampled, and so we have some issues there. So for the second case study, the Grizzly Creek fire happened in 2020 before we started a drone monitoring campaign. So that's the colors on this map are showing the burn intensity. And so we ended up trying to design this study to be a hybrid where, one, we look at what does drone scanning tell us about the slopes that we have lichenometric data for, but also what happened after the Grizzly Creek fire? Do we have more rockfall from these granitic slopes because of the wildfire damage? So we reused 3 sites from the lichenometry study, and then we have one new one that's our burn slope, which I'll show here. So on the left side, this is our burn slope. You can see the blackened trees. And we chose it because it was relatively close to a slope where we had lichenometric data. That's the one on the right. And these two have similar aspects, similar rock masses. And so we felt they would be a reasonable choice for comparing them to see, do we see more rockfall at one than the other? Or do we have a similar picture from those two? So, so for the second case study, it's in progress. These are a lot of goals that we haven't gotten to completing yet, but we're wanting to look at the comparison of burned and unburned slopes. We're going back to that quartzite and the granite slope, the slopes 1 and 2, along the highway that gave such similar rockfall recurrence estimates, and see, does that picture actually make sense based on drone scanning? So that'll help us with our soft validation of the lichenometric study. And then we'll also be able to look at change detection results from our source zone versus the talus. Do we get the same number of rockfalls if we do change detection on the talus as we do on the source? Because in the lichenometry study, we're using the talus as a proxy for our rockfall activity. So like I said, this is a year-long scanning campaign. We're aiming for monthly scans. It's been interrupted by the summer debris flows that you've probably all heard about. But I'll be continuing to collect data at least through next spring. I'm using a DJI Mavic 2 Pro, and I had a ground control network that I set up at each slope for the first scan, and then I'll be referencing every subsequent scan to that first point cloud. And I put these figures in to illustrate the flight automation that we're using. So to try to make our data collections consistent as possible, we're trying to fly the same flight paths, so automation helps with that. These are just, I wanted to show a couple photos of the debris flows because they're quite dramatic. But we've been able to get back in the canyon, and so once we process these scans, we'll be looking at, did that rainfall have any effect on rockfall? For the sake of time, I'm going to skip beyond the workflow slide and just talk a little bit more about our preliminary results. So, so far I have 24 scans of our 4 study sites. So slopes 1, 2, and 3, those are reused from the lichenometry study, and slope 4 is our new one. I've got a table to summarize all the many photographs taken so far, and there will be many more. So this is showing a couple of the change detection calculations. So the output you get is a point cloud where every point has a distance value associated with it. It's the distance between the 2 clouds at that point. So blue is into the page as we're looking at it, and red is out of the page. So what this is illustrating is that when you get these results, you've got to look through and do a little interpretation to see what do these results actually represent. So in this case, there's some vegetation that's showing up as a change out of the page. So that's not what we're interested in. We do have a rockfall over here that I'll zoom in on. So, so if we zoom in, we're seeing, all right, here's our blue marking that there's a change into the slope here. And so if we look at the photographs, what we see is this sort of crescent-shaped block marked by the pink arrow in the upper right is gone in the second image in July. And a quick volume estimate of that is about half a cubic meter. So that's the one rockfall I've seen so far in the data processing. Like I said, I have a lot of scans that I haven't even touched yet. So there's plenty more to do to look at the data. So in addition to that rockfall at slope 2, when I was setting up the ground control points, I saw there was a rockfall that happened while I was standing there watching it, which is pretty interesting. And it was also in that about half meter, maybe a little bit bigger, half cubic meter size range. We haven't seen any rockfall at the other slopes yet. There's a lot of data to process, but but so far, we're not seeing a lot of rockfall in the data that I've looked at. And this is even though these change detection intervals are spanning at least part of our thawing season. So what that might imply is that thawing is not, it might say that at these slopes, under their current geotechnical conditions, thawing is not as important for initiating rockfall. Or it might just mean that we're at a low background rate, and we're not seeing a lot because it's just happening at maybe a few year recurrence interval at these particular slopes. And so we might see some more after those September and October scans related to rainfall rather than thawing. So the rockfalls we've seen at the slope 2 so far are actually fairly consistent with the results that we got from the lichenometry. So if we go back to that recurrence interval plot, the half-meter size would put us at a recurrence interval around 3 to 4 years. And so if we're only seeing 1 or 2 of those in that kind of size range in a single spring season, that fits in fairly well with the idea that those would be on a couple-year recurrence interval. If we were seeing, for example, 10 half-cubic-meter rockfalls in a single spring season, then we might be more concerned that these lichenometry results are not so accurate. But so far, what we're seeing is somewhat consistent. But like I said, there's a lot of data left to look at. So just on future work, there's going to be a lot more scanning to do, at least through this next spring, and a lot more data analysis. And so what I'm hopeful we'll see is that we'll be able to fill out the picture of rockfall. We'll be able to have a really good sense of what did the lichenometry tell us that we believe, and we can definitely support it with other independent evidence, and where does it fall short, and be able to sort of put those thoughts together as we keep moving forward. So thank you all for listening. That was a lot, really fast, a lot to go through, but I appreciate your attention. And I'd be happy to hear your feedback and answer your questions. Oh, and by the way, I have a reference slide at the end here, but any of those literature methods that you're interested in, feel free to reach out to me, and I'd be happy to provide more papers if you want to look at anything like that. So thank you.